Yeah, we move on to Anna's talk now, who will talk about what barium stars can tell us about the S process. Okay,
you see my screen?
Yes, perfect.
Okay. Sorry. Yeah, so hello everyone. My name is Ana Escorza, and I want to start by thanking the organizers for inviting me to give this talk today. And what I want to talk to you about is barium stars, as Nicole said, but in particular, I want to convince you that these are good tracers to learn about AGB stars, particularly about binarity and nucleosynthesis. Just to put everyone on the same page and to start smoothly, I want to mention that AGB stars are low and intermediate mass evolved stars. So with masses, I don't know if you see my mouse, I guess this you see, with masses below around 8 solar masses. And the structure of these stars is quite interesting. This is a cartoon totally not to scale. And what we see inside these AGB stars is a CO core, which is the remainings of the previous core helium burning phase. We see a helium shell, a helium burning shell on top of the core, a helium-rich intershell that separates the previous shell from the other burning shell, which burns hydrogen. On top of this, we have a radiative layer that separates this burning area of the star from the huge convective envelope. And huge means huge. If I had made this cartoon up to scale in radius, we could not see the core. And why are AGB stars important? And not only for stellar astronomers interested in low and intermediate mass stars, but for astronomy and astrophysics in general? Well, the answer is that the helium-rich intershell that I just showed you is the main astrophysical site of the S process of nucleosynthesis, the slow neutron capture process of nucleosynthesis. So if we want to address big questions like the origin of elements, for example, we need to understand AGB stars, we need to understand the S process, we need to understand how these elements are made, because this process makes about half of the elements heavier than iron in our periodic table. So this is important for more than just stellar physics. Just to remind you how the slow neutron capture process works is because I will be the whole talk talking about this process elements. The way it works is the following. We have our original element, the nucleus of our original element, and we are in a neutron-rich environment. At the beginning of the chain, this nucleus will be iron. Iron is the seed of the S process of nucleosynthesis, which already tells you that this process is quite dependent on the metallicity of your AGB star. And what happens is that this iron seed captures a neutron in this neutron-rich environment, and this new nucleus is unstable against beta decay. Eventually, this reaction will take place, and this neutron will become a proton, and we have just made a new element like this. The chain continues, and we go capturing neutrons and decaying and capturing neutrons slowly and making all these heavy elements and some others. The S stands for slow. This means that the available neutrons is moderate, the amount of available neutrons is moderate, and that the beta decay is the transition or the reaction dominating this whole picture. In contrast, we have the R process of nucleosynthesis that is here in blue. R stands for rapid. This doesn't, it takes place in more neutron-rich environments. And what happens is that we capture many more neutrons before the beta decay transition happens, meaning that we make isotopes of these elements much more neutron-rich. With the S process, that is the one I'm talking about here today, we make the more stable versions of these elements. So, okay, AGB stars make all these elements, and this is important. The straightforward thing to do will be studying AGB stars, right? Like taking a spectra of AGB stars, doing atomic abundances of AGB stars, and figuring out in which quantities we make these elements, which parameters affect these quantities, and so on. The problem is that AGB stars are messy. I apologize if there are AGB-star fans in the audience, but AGB-star, I admire you all if you manage to get individual abundances of these objects, but AGB-stars are really complicated. They are huge, so already their parallaxes are not totally reliable, even with Gaia. They have huge convective envelopes that create these huge convective cells that change the stellar parameters that we measure in time. We also have very strong winds, we have pulsations, so the circumstellar environment of these stars is also quite messy, dust formation. And if we put these objects in binaries, we see these structures, we think they are in binaries, we cannot even prove it because even measuring radial velocities in these spectra is difficult. So additionally, they are very cold. They are on the top right of the HR diagram, which means that molecules start appearing as well. And again, measuring individual abundances in the middle of these huge molecular bands is quite complicated. I'm not saying it's not doable. There are great works there, but where I am proposing here is looking at the products of binary interaction, of interaction in binary systems that involve AGB stars, and in particular, barium stars, but there are others. Barium stars are these guys down here. They are not the only product of binary interaction with AGB stars. There are others, CH stars at lower metallicities, the carbon enhanced metal poor stars that also show enhancement in these S process elements, technetium poor S stars that are more evolved counterpart of these systems. And the way all these families form is more or less the same, is the following. We have a binary system with two main sequence stars. One of them, more massive than the other one, will evolve faster and will reach the AGB phase earlier than its companion. Time goes from top to bottom in my cartoon. This AGB star will make those as process elements in the helium-rich intershell that I showed you a couple of slides before. And the third redshift will bring those elements to the surface that then can leave the star and pollute the companion. The way this pollution happens is one of the biggest questions concerning this type of objects. We are not sure yet. It could be wind pollution, it could be Roche law overflow, although Roche law overflow, when you have a star with a huge convective envelope, is not really stable. We could involve third agents, like for example, a circumbinary disk around the system. But in any case, I'm going to go one step further. I'm going to say that these stars form and that we are analyzing them down here. So we look at these systems after the AGB star has finished their evolution. It's become a white dwarf and it's cooling down. In fact, in most of the systems, the white dwarf is not even detectable. And what we want to do is analyzing these objects observationally as well as we can, in order to learn as much as we can about the previous phases, about the AGB star itself and the S process of nucleosynthesis, but also about the interaction between the AGB star and its companion. And this question is not new. This is not a proposal that I'm coming up with just this week. There's been a lot of work since barium stars or the other related families were discovered. There's been a lot of work trying to use these objects to understand the AGB phase and to understand the interaction of AGB stars with the companions better. What we have done new or recently, or what we have that they perhaps didn't have before, is Gaia. So we have done a lot of effort in the last 4 or 5 years during my PhD mostly, trying to, as I said, characterize these barium stars observationally the best we can and produce a good collection of observational constraints that can help us learn about these previous stages. So what can barium stars help us with? The orbits, these orbital parameters of systems like this need to be reproduced by your binary evolution models. If you take binary population synthesis models and evolve star binary systems all the way to the end of the AGB phase, or to the end of the post-AGB phase, the orbital elements that you bring out of that need to be close enough to these Barium star systems, because we know that they form this way. Additionally, the S-process abundance pattern on these stars, so the abundances of these stars, which are less difficult to measure than the case of AGB stars, need to be reproduced or at least close by AGB nucleosynthesis models, because it was made by an AGB star, right? So it can also help us constrain other effects, like, for example, dilution when the mass transfer happens, but the abundances are there and are still visible in the red giant phase. So something keeps those elements visible on the surface. Additionally, the masses of these two stars are useful information as initial conditions for these two set of models. What I'm going to show you now is those observational constraints that we have been working on for the past few years. And I'm going to focus on the orbital properties of Barium stars, the HR diagram and their masses, and the wider masses that we are working on. So to start with the orbits, I'll show you a radial velocity curve of one of the objects that we've been studying. In order to fit radial velocity curve, in order to model the radial velocity curve of one of these Barium stars, you need a huge observational effort because they are wide. These systems hosted an AGB star not too long ago, so the orbits are long. This is not even one of the longest ones. I'll show you the whole sample in a second. So we combine Hermes radial velocity data. Hermes is a high resolution spectrograph mounted on the Mercator telescope in La Palma, and it's been monitoring evolved wide binaries for 7-8 years now, probably. So we combine these data with older data from previous monitoring programs for this type of stars, or archival data of other kind, or with salt spectra when we couldn't reach it with Hermes from South Africa. So for the southern objects. And combining all these data, we could fit the orbits of about 130 dwarf and giant Barium stars. Some of them were known before. We have just done, well, we have improved the long orbits. We have fit all most of the dwarfs, and we have collected this sample to have a full family picture here. I mentioned before that one of the biggest questions concerning Barium stars were the orbital parameters, how the mass transfer takes place and how that shapes the orbital parameters of these systems. And just to show you how bad this is, although I mean, I'm going for the exaggeration a bit here because there are works that have improved this picture before, but I want to show you the general picture of what happens if we try to model Barium stars, if we try to produce Barium stars with population synthesis models using standard binary interaction physics. So nothing fancy, no circumbinary disks, no wind roach flow overflow, just standard binary interaction. And what Robisard observed in 2010 is that Barium stars, if they formed via roach flow overflow, we expect that the orbits shrink and circularize. So we will expect, to observe these objects down here, zero eccentricity and short periods. On the other hand, if these objects form via wind mass transfer, we expect the orbits to widen, and we will only observe eccentric systems at longer periods than about 2000 days. You can see that what our data shows is not that. We have eccentric objects much earlier than this, and the models even predict a period gap that we clearly populate. And this is not an issue only of Barium stars. If you plot post-AGB binaries, for example, on a NILOC-P diagram, they will populate a similar area, and the models also cannot reproduce those. As I said, there's been a lot of work concerning circumbinary disk, wind roach flow overflow, but the orbits of barium stars have not fully reproduced yet. So hopefully these observations can help in that aspect. One more thing that we can get when we work with spectroscopic binaries is the mass function. The mass function is this expression over here that relates the orbital parameters that I just showed you of them, and this k is the semi-amplitude of the radial velocity curve that I showed you before. So we have this. And this mass function relates this with the masses of the two components in my binary system and with the inclination of the system. So we have a star that we see, and we can almost treat it as single for this. That's an assumption that we had to make it there. Because the white dwarf is not visible in the optical spectrum, and the orbits are quite wide. So we treated this star as single and try to determine its mass. I will show you that in a second. The last parameter that we could learn something about is the inclination, and I will also show you at the end how we are working to get these inclinations. If we manage to put all these ingredients in this equation, we will get the mass of the other component as well, the one that we cannot see. Let's get first the primary mass of these barium stars. I show you here the Hertzsprung-Russell diagram of barium stars. Again, lots of data and lots of work in a single plot. We used Hermes spectra to determine the stellar parameters of these stars when they were in the north. When they were in the south, we used literature parameters or archival data. And we determined the stellar parameters like this. Then we used broadband photometry that apparently I don't list here, in order to fit an SED as well. We did this with Mark mobile atmospheres. And then we used the Gaia distances in order to get the luminosity and be able to plot them on the HR diagram. Finally, by comparing their location on the HR diagram with a grid of startable evolutionary tracks, we determine the mass of these objects as well. This is the mass distribution of the barium stars in our sample, those 130 systems that I showed you in the previous plots. And the first thing that we observed is that these two samples that we considered evolutionary related don't seem to be so. We see that the dwarfs have somehow significantly lower masses than the giants. It's true that it's not trivial to get the mass of these stars over here, but already from the HR diagram, we can see that these guys have lower masses. We think that this is because there is a strong observational bias against finding these objects at hotter temperatures, also because that region of the HR diagram is populated by a lot of type of chemically peculiar stars that could hide these objects. In any case, we are working, and we're working on this, and we have found a few stars that will shift our mass distribution a little bit to populate the main peak of the giants. But I'm not going to enter into that now because I want to show you the white dwarf masses that we are working on at the moment. This is where we are now. We have the mass function value from the orbits, and we have M1, we have the masses of our primary stars from the Hertzsprung-Russell diagram and the evolutionary tracks. And now we want to get these inclinations, and the way to do this is including astrometry. It's a great time to try to do this, and we are also lucky because our stars are bright enough that most of them, a lot of them were observed by Parcus as well. So we can combine the power of the two most famous astrometric missions and try to get these wider masses by combining them. So this is work in progress at the moment. We are following the methodology used by Rob De Rosa and Timothy Brand and other groups that they normally use these to determine the mass of planetary companions of these type of stars, white planets or planets in white orbits. And we are just using their methodology in order to get the white dwarf mass. And the way this works is the following. We use the radial velocity data that we have, and we are very lucky because we have a lot. We combine this with the Hipparchus and Gaia acceleration, so the proper motion at the time of the two missions. And we combine this with the Hipparchus astrometry, the individual epoch astrometry when possible, and one single orbital model, including the mass information, needs to reproduce, needs to fit all these data. We can put the primary mass as an input, and it is good enough for me to tell you that, for example, this target has a companion, a wide-earth companion of about 0.58 solar masses. As I said, this is work in progress. We will hopefully submit this soon, so stay tuned for more masses if you're interested. And why you should be interested? Why are these masses useful and important? Well, stellar masses are useful and important always because they affect absolutely everything that happens to the star. And I recommend you this review on mass determination across the HR diagram in case you are interested in stellar masses in general. But in the particular case of Barium stars and their wide-earth companions, well, as I said, the mass ratio of these systems is an important initial condition for to learn how these systems actually form. We can also combine the abundance pattern on the Barium star with the wide-earth mass and learn about the process of nucleosynthesis. We will see if we can improve the models, or if we can understand better what's going on inside the AGB-star by combining the pattern of the chemistry and the mass of the white dwarf. If this is going too far, perhaps at least we will be able to say something about the different white dwarf companions that different Barium stars have. Barium stars have been historically divided in strongly polluted or mildly polluted. So if we find differences between the white dwarf companion of those two samples, that already will teach us something. And if we try to do this and nothing makes sense, then perhaps we will learn about the initial final mass relationships of these type of objects, or see if in binaries it works differently. So there is a lot to learn just by looking at all these data. So this is just my summary. What I've done in the last 20 minutes is plugging numbers in an equation. We have orbits from mainly Hermes and some other instruments. We have primary masses thanks to Gaia distances and to a lot of other data. And astrometry is helping us to put the last ingredient in our soup in order to get these masses of these invisible white dwarfs. So going back to the question I threw in my title, what can Barium stars tell us about binarity and nucleosynthesis in AGB stars? Well, they can help us put constraints on the initial conditions of all these models. They can help us put constraints on the dependencies of the S process of nucleosynthesis with mass, for example, or with metallicity. And I only mentioned these before, but depending on what we find, perhaps we discover that dilution is more important than what we thought, that more mass transfer was said, and well, there are a lot of questions that we can address with all these data. So I thank you for your attention now, leave you my contact and a few papers, and yeah, I will answer your questions.
Thank you very much, Ana. That was a very clear talk, and also congratulations on your nice slides. We already have two questions. First one is from Marcelo. He is asking, how sensitive are your red giant masses to metallicity? Given that they are derived from the location in the Hertzsprung-Russell diagram, I would expect that to be not negligible. How well do you know the metallicity?
Yes, we actually so I put one HR diagram there with my one random set of tracks, but to determine the mass, we use Mark model atmospheres of the adequate metallicity after determining it from the spectra. And we use the evolutionary tracks of the correct metallicity as well to determine the mass. So there is one single plot there, but in the paper we showed, I don't know if 2 or 3, we divided all our samples from 0, minus 0.25, and minus 0.5, I think it was. And we determined the masses using the appropriate metallicity, the spectroscopic metallicity. So we did the best we could, but indeed, in the previous work that we did in 2017, we analyzed this issue and we realized that it was something that we definitely needed to take into account.
Okay.
Thanks.
The other question is from Roberto Radi. He asks, first question, is there a chance to identify higher mass dwarfs, or is there also some evolutionary bias in addition to the observational bias?
I am not sure. I don't know how far up in the HR diagram we can get. I have found a couple of early F, late A type stars, so there is definitely an observational bias. There are some S-process enhanced stars there, but most barium, so we think that the progenitors of all these barium stars are low mass AGB stars because of the type of the S-process pattern tells us that is probably the progenitor AGB star is probably of a mass of around 3.5 to below that. So we cannot go really high up in the companion mass because the other one had to be more massive to evolve earlier. So I'm not sure how massive of a barium star we can find.
Okay, and the second question is, could a search for barium stars among open cluster blue stragglers help with this issue?
Yes, is also there in my to-do list, and I'm working now with a collaborator that has a lot of cluster data and is interested in looking for this type of star on those clusters. So yeah, it's definitely something that we'll try to address as well.
Okay, then just thanks from Roberto. Then I want to ask a question myself. Do you also derive the masses via surface gravity times radius squared divided by gravitational constant? So when you have with Gaia, you can, when you do a SED fit, derive the radius, and then I assume the errors on the surface gravity might not be that big. So did you try to derive the masses?
I didn't try, no. I thought of it and we discussed it at some point, but no, we never did it actually. Maybe we should do that check, yeah.
Okay, and then are there any other questions? Then please raise your hand or write in the chat. Don't think more are coming. So let me thank you for your talk again, and then let's go to the breakout sessions. And let me find how to end this. Here.